of 9.76, the charge of the solution is -2. And then at a pH we're going to calculate the charge of the solution is -3. So you can actually change the pH to determine the charge of the solution. And we'll do an application of this. Actually, you did an application of this last week when you prepared those buffers. So, for example, note that you can make about a pH 2 buffer using H3PO4 and H2PO4 minus. This is your first buffer region. Your second buffer region is about 7.2. So you'll use H2PO4 minus and HPO42 minus in your buffer. Then at a pH around 12, you'll use these two substances to make a higher pH buffer. Okay, so PO43 minus is present at the third endpoint, but is this a strong base or weak base? Strong or weak? Yeah, so to figure this out, we have to do that base hydrolysis reaction. We have PO4 3 minus reacts with water, and the products of this reaction are and then you want to calculate KB. So remember that KB is equal to K W divided by KA. Okay, so what are the products of this reaction? Okay, so it's going to be HPO4 2 minus plus OH minus. Now for this, to calculate KB, is this going to be Ka1, Ka2, or Ka3? Okay, Ka3. Okay, so this Ka refers to this acid here. Okay, so then once you get we'll do what we did before. So when you do the initial amount, the amount that reacts, amount of equilibrium. So before we do that, what's going to be the concentration of PO43 minus at the third endpoint? Is it going to be 0.1 molar, which was the concentration of phosphoric acid before you start the titration? It's going to be 0.1 molar. Yeah, so we want to figure out the initial concentration of phosphate so we can do this calculation. Is this concentration going to be 0.1 molar? Okay, now what's happening is that you're adding base in the titration. So if you start with 20 milliliters of 0.1 molar phosphoric acid, titrated with 0.1 molar sodium hydroxide, what volume of NaOH is needed to get to the first endpoint? So this volume here is going to be not 40. 20. And then at the second endpoint, this is going to take another 20. So at this point, this should be 40. Then at the third endpoint, this should be 60. So note that in between each endpoint, it should take the same volume of base. So if you start with 20 milliliters, okay, so again, you're starting with 20 milliliters of 0.1 molar H3PO4. Now you've added 60 milliliters of the NaOH. Now we have a total of 80 milliliters of solution. So what's going to be the concentration of the PO4 3 minus? So to do that, note that a dilution is occurring here. So we've got to use our dilution equation. So in our dilution equation, okay, so we have C original times V original equals C diluted times V diluted. So when we plug in our numbers, we have 0.1 molar, and then what numbers we put in? What numbers we put in there? Here and there. At 20. Yeah. And this is C diluted. So we want to find that. So let's solve for C diluted, and that's equal to 0.025. So that means that for our initial concentration of phosphate, this is 0.025 molar. Okay, so we can do what we did before. Now, let's calculate Kb. So Kb is going to be, let's see, so Kb is going to be 1 times 10 to the minus 14 divided by Ka3, which was, Ka3 is 4.8 times 10 to the minus 13. So Kb is equal to
2.08 to the negative 28.
I think this part, check your exponent again. So 2.08 times 10 minus. Yeah, because see, 10 minus 14 divided by 10 minus 13, that's like 10 minus 1. So this should be 2.8 times 10 minus 2. Okay, so we know what Kb is. And now we can do our equilibrium calculation. This is going to be 0.025 minus x, and x. So now we can plug it into this equation. We have x times x divided by 0.025 minus x. Can we use our assumption here again? X equals 0 in the denominator. Because note that this number is actually close to that one, but just to make it easier, we're going to do it anyway. This is negative y. Okay, so for example, on a test or exam, if you forget to do this, that's okay. You'll get almost all full credit. Then if you do this, that's okay too. Okay, it just makes the calculation easier. Okay, so anyway, we'll solve for x and see what we get. So let's see, so George, you got for x, you got, what was it again, 0.23. So note that this is also equal to the OH minus. So when you do the, calculate the POH, that's equal to Pardon? 1.6. And then the pH then is equal to, so 14 minus that, that's equal to 12.3. Yeah, so note that at the third endpoint, that's 12.3 or 12.4? 12.4. So the third endpoint, that's 12.4. So note that according to our calculations, at the halfway point and the third endpoint, they're very close together. And the reason for that is because we had to make that, we probably shouldn't have made that simplifying assumption here. So that's probably, it's probably a little bit off. That's okay. It's close enough for what we need to do. Now I know all of you love math, so this is just absolutely sheer beauty. Look at that. Look at all that stuff. All those numbers and all those symbols and a graph to.
You missed the symbol.
A graph in there too.
You missed the minus of the HQPO4.
Where?
Minus.
Where?
HQPO4.
H2. Oh, okay. It's not even better. So I heard from one of our math teachers that during the math academy, what they the math academy students chant, I think it's eat, sleep, math. Excuse me. I got this funny taste in my mouth. Okay. Let's go to the next slide. So, weak acids and bases are found in biology. So, I heard in Bio 1 you guys do an electrophoresis experiment. So, that's a lab technique used to separate and purify substances based on charge. So in this technique, you can purify amino acids, proteins, DNA, things like that. Let's take a look at these two amino acids, histidine and lysine. What we'll do is we'll draw the structure of each amino acid. We want to figure out how many protons are donated by each amino acid. We need to look up the pKa values of each of these amino acids. At low pH, what's the charge of each amino acid? At what pH does the amino acid have a charge equal to 0? That's called the isoelectric point. And then, based on this information here, we can figure out the pH to set the solution at so that we can separate the histidine from the lysine in this electrophoresis experiment. Okay, so really in electrophoresis, what you do is you have these two plates. Okay, so for example, let's say this is your mixture. And you have a negative electrode here and a positive electrode there. Okay, so these are connected together by some circuit. So all the positively charged substances will migrate toward the negatively charged electrode. All the negative ones will migrate toward the positive ones, and that's how you can separate one substance from another. Okay, so before we start, let's actually take a look at this website and find the pKa's. But before we do that, in chapter 22, I think, it shows the structures of the amino acids. Let's see. Yeah, so take a look at table 22.2 on page 768, and it shows the structures of the 20 amino acids. So we want to look at histidine and lysine. So what we'll do is I'll have half of the class do histidine, the other half will do lysine. And what you want to do for each one is draw a titration curve for your amino acid. Okay, so which half of the class wants to do histidine? I know it's a hard choice.
What page again?
Table 22.2, page 768. Okay, so we'll have this half do histidine. And then the other half will do lysine. And while you're drawing the structure, let's look up the pKa's of these amino acids. Okay, so let's do that.